right, here we go, pre-calc kids. So this is in our new packet. Remember, our new packet is chapter 6. So this is 6.1 part 2. But before we kind of get into like the second part, I just want to review for like a quick minute what part 1 was about. And remember that part 1 matched problems on the homework 1 through 8, right? So what part 1 was all about was this definition of derivative, but it was a definition of derivative at a specific point. And so the reason we do limits before we get into derivatives is because part of the definition of derivative is going to contain a limit. So remember, that's what this f prime of c notation is. So this little tick mark in the upper right hand corner, you read it as prime. So f prime of c is equal to the limit as x approaches c of f of x minus f of c all over x minus c. And all it really is slope. This is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. But the idea is you're trying to approach that c value, because instead of the slope between 2 points, which is called the slope of a secant line, you're finding the slope of the tangent line, or the slope at an instantaneous rate of change, right at an instant. And that was like the one thing that I wanted to come back and remind you of, that when we're using this first definition of derivative at a specific point, right, where point P would be the c comma f of c input comma output, where our x is approaching c, then this is the definition of derivative at a certain point or at a certain instant. It's also the same thing as the slope of the tangent line at point P. And it's the same thing as the slope of the curve at point P. They both share this same point of tangency. So make sure you're taking good notes on this stuff, because I tried to say in the last video, like, this is the part that confuses a lot of kids in calculus. Like, you're saying different things, but they mean the same thing. So you kind of got to get down to this stuff all means the same thing. So your tangent line and your curve share the same point of tangency. And I know it might kind of seem weird to think about a curve having a slope, but you can have like an average rate of change between 2 points on a curve, and that secant line is a close approximation of what the slope of the tangent line is. But if we really want to know what the slope of the tangent line is at a certain instant, it's all about finding the slope of the curve at point P, or the slope of the tangent line at point P. So like, that's another thing to kind of like keep in mind. It's kind of like at a specific instant when we think about this definition of derivative and find f prime of c. Okay, so all those things mean the same thing. And if the limit actually exists and you can actually find it, but remember, to find it you're going to have to finagle, and it kind of kept happening that you had to finagle, then the derivative exists and you can find that derivative at a certain point, and that gives us our slope of our tangent line. And then if we know the whole point, sometimes we had to find the y first, then we have our whole point and we have our slope, and then we can write the equation of the tangent line. And that equation of a tangent line is really close to what's happening at the curve at that same point of tangency. But this one's just not quite as powerful as another formula. So we're going to talk about the more powerful formula that we're really going to start using way more often. So this one is nice, but it just gives you the slope right at that instant, right at that c value. And it's only telling you like the slope of the tangent line and the slope of the curve at that one point. So it's not as powerful as finding the slope in general, or finding the derivative in general, or in terms of x. So then we can use it to find the slope at any point. I just crashed into a carton of Red Bull that's sitting here on the floor by my whiteboard, Mr. Herney. Maybe like he should move his trash, right?
By your whiteboard, it's my whiteboard.
It's my whiteboard. All right, so I'm gonna go ahead and write the formula up, and then we will draw a picture and I'll explain like where it comes from. But as I'm writing the formula up, I'm hoping like a little light bulb clicks off and you're like, I feel like I've seen part of this before. So again, we're finding the derivative, so we're going to do f prime. A lot of times we're going to be in function notation. This is the easiest of derivative notations. We're going to learn others along the way. This one we start with is because it's the easiest. And if it's the more powerful formula because it's in general in terms of x, then it's f prime of x, not f prime of a certain number c, right? That's at a specific point. So f prime of x equals the limit, because we still have limits going on, but this time it's h approaching 0 of f of x plus h minus f of x all over h. Oh, doesn't that fraction look somewhat familiar? Like maybe you just did it on your test? And when you're finding the derivative and finding the derivative in general, that's called differentiation. So Mr. Hardy was talking to you about how in calculus there's kind of like three main parts. You have limits, you have derivatives, and then in the spring in calculus we learned about antiderivatives or integration. So the first branch, the main branch of fall semester calculus, is differential calculus, or differentiating, or finding a derivative. Again, all those words kind of mean the same thing. So this is just a way more powerful formula because it gives us a derivative in terms of x, and then we can plug in any x we wanted to find the derivative at a certain point, but we could keep changing up the point. So it's a much more powerful formula. So before we do examples and we use this formula, just a little picture of what's happening, right? Giving you the visual. So if I just drew mostly like quadrant 1 on a graph, and I just took something nice and smooth and connected that was continuous everywhere, like probably a portion of a polynomial, and I said, okay, let's look at a spot. So if I wanted to say, okay, here's a spot on my graph. So like here's point P, and I'm going to label this as point Q. Okay? And let's say that point P is the spot x, comma, f of x. Okay, so here's my x value. And I'm kind of zoomed in on this because that's totally empty, kicking it out of the way. Because I want to make sure you guys can see it. But the idea is pretend that it's small. Then I'm going to trip on that side, Ernie. So let's say that I want to move away from x this distance of h. So if I want to move this h distance away to put me at point Q, and I say, okay, so then what's the ordered pair here? A lot of you be like, but don't make it hard, right? You've moved h distance away to the right. Isn't the x part of the ordered pair x plus h? And don't you plug in an input to find an output? So if this is our nice, smooth, continuous, connected portion, let's say of a polynomial, and we say that this is the graph f of x, then wouldn't this be f of x plus h? And so if you kind of have down, at least at this point, oh, well, a derivative is all about slope, and I just thought about finding the slope. Like you know how to find the slope, the rate of change, the change in y over the change in x. And I said, okay, well, so here's my y sub 2. So I would have f of x plus h minus, here's my y sub 1, f of x, over, here's my x sub 2, x plus h, minus x. Oh, look at that. Some nice things happen. And in the denominator, the x's cancel. And we're only left with h. Oh, isn't that interesting? And if I really want to not find the slope of the secant line, because right now I'm connecting an endpoint to an endpoint, and this is called the slope of the secant line, but I really want to find the slope at point P, right here, at this instant, don't I want to actually keep bringing this in, and bringing this in, and bringing this in, so Q gets closer, and closer, and closer to point P. And that idea of like getting closer, and closer, and closer to something is the whole idea about a limit. So how about we limit this, so there is no distance h. That's why we're doing the limit as h approaches 0. If we really don't have a distance that we are away from point P, then we're going to find the derivative in general terms, in terms of x, at an instant on our graph, in general on our graph of f of x, so we're finding f prime of x, and then we can plug in any c or x value we want to plug into and evaluate it. So that's really where this powerful formula comes from. So you will have to get this down. So this is still the definition of derivative, but it's the more powerful formula where you're getting the derivative in terms of x, in general terms. So you could use it for any instance. And when we get ready, which is a long ways away, but when we actually get ready to have a test, when we have a test over this stuff, you'll have to do a problem by definition of derivative all the way through. And then we'll learn other ways to do it, kind of like with limits, like learning all that crazy notation, right? And then you understand and you appreciate the notation so you can go to the shortcut kind of ways. Same idea here. So I'm going to keep that up on the board, and we're going to start doing examples for part 2. The calculus and learning the formula with the limit as h approaches 0 of f of x plus h minus f of x all over h, the calculus won't be hard. The hard part will be finagling the algebra. It's always the algebra that's going to screw you guys up. It's not going to be the calculus. So first example, let's say that we have f of x equals the square root of x, and we're supposed to find f prime of x. And right now, the only way that we have to find it is to try and do the definition of derivative in general. So notice that I'm not telling you to find the derivative at a certain point. I'm just saying find f prime of x. So this is the general terms. It's actually going to give us the same answer if we pick a certain point as the one that is definition derivative at a point. But the idea is we a lot of times just want the derivative in general terms. All right, so we know to find f prime of x, we need to take the limit as h approaches 0 of f of x plus h minus f of x all over h. That's why we kept trying to drill that part into your head before and test it on you on that part, just the quotient part, because we knew it was coming up in section 6.2. So we're going to substitute in, and we're not substituting in numbers yet, so we got to keep our limit notation, right? The limit as h approaches 0. Well, f of x plus h, doesn't that mean go to the rule f? Here's my rule f. Wherever I see an x, there's only one x, which that's thankful for. I have one term. We're also thankful for that. Aren't we plugging in the whole quantity, x plus h, in place of the x? So I know my rule for f has the square root, but I'm replacing this with all of the expression x plus h. So all of that's under my square root. Minus, again, we're lucky in this case, because f of x is only one term. So we can just write minus the square root of x. But if this had been more than one term, wouldn't we have to do minus parentheses and distribute the negative through? So watch for that. And don't lose your denominator. I don't know if Mr. Herney feels the same way as I do, but I feel like so often, because the algebra gets so intense, you guys are working so hard and you keep losing this guy. Don't be surprised, you guys, as you're going through homework, if your definition of derivative in general is taking you at least a half a page of paper. Like, it's going to take you a long time. Herney and I were just looking at his answer key for a certain problem, and he had a whole sheet of paper for one problem. So you got to space it out. You got to keep it straight. You got to have good notation. We're still grading on notation, okay? So what's the first thing that we try with limits, Mr. Herney? What's the first
Direct
thing?
sum.
Direct sum, right? But just like it was on definition of derivative with a specific c value, because when you plug in 0, isn't 0 always going to give you division by 0 for h? Notice we're doing as h approaches 0. You're plugging in the 0 for h, okay? So we definitely get 0 in the denominator, which is a big fat no-no. And if I thought about doing it up top in the numerator, just mentally in my head, x plus 0 would just give me x underneath my radical, so my radicand would be x, so I'd have square root of x minus x, and the numerator also equals 0. So that means I have 0 over 0, and direct substitution's not just going to work right off the bat, so we're going to probably have to do some sort of
Finagling!
But in this case, it doesn't look like factoring's going to work. Like, what are you going to factor? So maybe, you did this last chapter too, we should try a thing with conjugates. I mean, if you have radicals going on and there's two terms, conjugates kind of seem like a good place to start. So if I have two terms, I'm going to go ahead and encompass those in parentheses for those two terms. Wouldn't my conjugate be the same exact two terms, the square root of x plus h and the square root of x? And the only thing that would be different would be the sign in the middle. So the conjugate is the square root of x plus h plus the square root of x. But if I'm going to multiply my fraction with the numerator's conjugate to keep it an equivalent fraction, I got to do the same thing down below to my denominator. And I haven't evaluated the limit yet, because I haven't substituted any numbers yet. I haven't found f prime of x in general yet, because I haven't evaluated the limit yet. I'm just trying to finagle. So everything about my notation stays the same. Left-hand side is still f prime of x. And typically, if we were in the classroom, I'd have a lot of questions where people will say, oh my gosh, do we have to write that every time? And usually I would say, well, no. If you write it at the top and you like draw an arrow down or do little like quotes down, I'll know that you're following it down. But make sure and get it back at the end, okay? But this side, you can't just kind of like be all over the place. You need to keep it, if it's a fraction, in fraction form. You need to keep the divide by h. You need to keep the limit until you're evaluating your limit and you're able to get rid of your bad factor and substitute. So we have the limit as h approaches 0. Okay, we're going to go ahead and multiply our conjugates out. And remember, at least when I always talk to my kids about this, if you know their conjugates, you know nice things should happen with their product. So the square root of x plus h times the square root of x plus h, wouldn't that just give me x plus h? The outside and the inside are going to cancel. I would not write them down. You'll get confused. You'll like not know what order to put them in. You'll get all like flustered. Why do you need to do that? You know it's the exact same two terms times the exact same two terms, and one's positive and one's negative. They cancel, don't even write them down. And the last would be a negative square root of x times a positive square root of x, which would just give me negative x, right? Square root of x times itself would be the square root of x squared, or just x. And in the denominator, we actually probably don't want to multiply it out. We probably want to leave it in factored form. The conjugate part, yes, multiply through. Nice things should happen when you get their product. But the other part, just leave in factored form. Plus, think about it. Isn't our whole issue that this is division by 0 from this h factor? So maybe if we leave it in factored form, we can somehow cancel that factor out. Well, nice things start to happen, just like we talked about when we were just doing only this part before the limit part. Oh, everything should cancel if you've done it correctly, except for things with h's in it. Oh, look at that. Everything canceled except for things with h's in it. And now I have f prime of x, or my derivative in terms of x, equals the limit as h approaches 0 of h, only left on top, over h times the quantity x plus h underneath the square root, plus the square root of x. That's why we left that in factored form. Because now if it's all in factored form, it's all multiplied. This h is multiplied with all of this. Then can't we reduce out these common factors? But notice, you guys, when I reduce the h's out, there's still something left on top. The location of this stuff is on the bottom. The stuff that's left on top is really just an understood 1. So we have f prime of x equals the limit as h approaches 0 of the fraction 1 over the square root of x plus h plus the square root of x. I'm not even going to use parentheses anymore because that bad factor went away. And my fraction bar is kind of like grouping all of these two terms down in the denominator for me. And if I just got rid of my bad factor, then shouldn't direct substitution work? So I'd have f prime of x equals, now I am going to drop the limit notation because I'm evaluating the limit. I am taking the limit. So the 1 in the numerator is going to stay. Remember, it's as h approaches 0, so you're replacing every h you see with a 0. The square root of x plus 0 plus the square root of x. Well, x plus 0 would just be the square root of x underneath there. And if I have square root of x plus the square root of x, those are like terms, aren't they? The same root, the same index, square root, with the same radicand underneath. This is 1 square roots of x plus 1 square roots of x. Aren't they the same power, the same root, with the same radicand underneath? So they're like terms. So don't I have 2 square roots of x? So my derivative, f prime of x in general, would be 1 over 2 square roots of x. So now your answers are going to look like this answer in terms of x instead of a particular number. But the powerful thing about that is, okay, just to show you, is if now I said, okay, let's find some derivatives at a specific point for this function f. If I said, oh, I want to know the instantaneous rate of change when f on the function when the function c value that your x is approaching is 1. Then if I wanted to find f prime of 1, I could just plug 1 in to this generalized formula. Oh, it'd be 1 over 2 times the square root of 1. Square root of 1 is 1 times 2. Oh, this would be a slope of 1/2 at the instant when x is 1. It's the derivative at 1. It's a slope of the tangent line at 1. So the slope of the tangent line is 1/2 when x is 1. It's a slope of the curve 1/2 when the x is 1. It all means the same thing. But then if I wanted to change it and I said, okay, find the derivative evaluated when you have a value of 9. Find f prime of 9. Oh, that means to find the instantaneous rate of change of my rule for f when x equals 9. That means to find the slope at 9. So I take the derivative in general terms and I just substitute in 9. So the square root of 9 would turn into 3. 2 times 3 would give me 6. So the slope would be 6. But the slope would equal 1/6 when the x value was 9. So it's a different slope when the x is 1 versus when you're at 9, which makes sense, right? You're moving along this curve and you're moving at different rates of change. Okay, so that's why that formula is so much more powerful. We can get the derivative in general and then plug in a plethora of points that we wanted to plug in. Okay, so there's first example. And it reviewed how to do some finagling with conjugates. So hopefully that was like a really good review. All of this calculus part builds on each other, you guys. So if you didn't get the prior chapter, you're going to struggle in the next one. You got to get the stuff previous to be able to kind of move on. Okay, still keeping my rule up there and my kind of visual graph of like what we're doing and why it works. And now we're going on to example number 2. Okay? So example number 2, we want to find f prime of x, or the derivative in general terms in terms of x, if f of x is equal to 1 over x squared. So if you just think about it graphically, 1 over x squared is a rational function with a vertical asymptote on top of the y-axis, or at x equals 0. But instead of being in alternating quadrants because it's x squared, wouldn't x squared always give you a positive answer out, so it looks like a volcano graph like this? Your horizontal asymptote is on top of the x-axis where y equals 0 because our degree on bottom's bigger. And we're just finding the idea of, oh, it's the slope of the curve in general, and then if we want to plug a certain point in, then we're finding the slope of the curve at a certain point. So like if eventually I wanted to plug in, let's say 1, that would be the slope of my tangent line at 1, or that would be the slope of my curve at 1. And we would be focused on like that one particular point, zooming in on that one point. But if we're finding f prime of x first, because that's more powerful, we're finding the derivative in general. So here we go, right? Oh, f prime of x, the definition of derivative in general, is the limit as h approaches 0 of f of x plus h minus f of x all over h. So the more that you're writing that down first, the more you're going to drill that definition of derivative into your long-term memory. And by the way, you're going to notice that as we're going through this section, the functions we give you are very basic, because if we didn't give you very basic functions and there were lots of terms and lots of x's and lots of stuff you had to replace your x with x plus h in, this gets even nastier than it already is. So yes, some of you are going to feel like this is so much work, this is so time consuming, there's got to be a better way. There's going to be a better way, but you can't do the better shortcut way until you appreciate the definition. Right, Mr. Herney? Tell them they need to appreciate it.
There is no better way. This is the only way.
So the limit as h approaches 0. So f of x plus h means go to my f rule. Here's my f rule. Wherever I see an x, thank goodness there's only one x. It's in the denominator though. Are we going to have to write x plus h in place of that x? So it's going to be the fraction 1 over something squared, but that something squared is x plus h, right? If this were 8, you would plug in 8 for the x and square the 8. It's the same idea. You're just plugging in this whole two-termed binomial expression. Minus f of x. F of x is the original rule we had. Our original rule we had is only one term big. It's only 1 over x squared, so we can just do 1 over x squared. If it's more than one term, you have to do minus. I usually do brackets to like emphasize that I have to subtract all of it. But if it's only one term, minus that one term. All over h, and this is even more of a example where more kids lose the h because you got fractions already going on, and then you have the denominator of your great big fraction. Ooh, nasty. So in order to find my definition of derivative in general, because right now, of course, this is going to give me division by 0. If h is 0 and I try and do direct substitution, that's what we try with limits approaching a c value. This is going to give me division by 0. And up top, if h is 0, then I would have 1 over x squared, which is just the fraction 1 over x squared, minus 1 over x squared. That's a numerator of 0. Then we're going to have to do some finagling. But if we have fractions embedded inside of fractions, kind of seems like maybe we need to get one fraction over one fraction. So we can do a little copy dot flip. So don't we want to get these two to become 1? Which means I need a LCD. So what at my lowest common denominator, I like to kind of put them in order, be this single monomial piece, x squared, times, because you don't need to write this out twice and FOIL it. What are you doing? Right? Denominators we like in factored form. Don't we need, though, this whole quantity raised to the second, so every single denominator's factor is accounted for. So we would have x squared times x plus h, the whole thing squared. That would be our LCD. So this fraction is just missing the x squared part. But whatever I do to produce LCD in the denominator, I got to multiply by the same thing up top to the numerator. And this fraction is missing the whole quantity, x plus h, the whole thing squared. And whatever, again, I do to produce LCD in the denominator, I got to do the numerator. And then you just got to be careful not to lose that other h that's still hanging out right there. So we would have f prime of x, or the derivative in general, equals the limit. We're finagling right now. We're not ready to take and evaluate our limit. We got to get rid of our bad factor. So the limit as h approaches 0 of x squared over the x squared times x plus h, the whole thing squared. The denominator is in factored form, minus, and then we have, I'm going to go ahead and think about this as 1 times x plus h squared. Well, multiplying by 1 doesn't change anything, so just x plus h, the whole thing squared, over x squared times x plus h, the whole thing squared. And then that's all over the h from the original fraction and the original definition of derivative. See what I mean? Taking full piece of paper, all these fractions vertically up and down. All right, so the reason that we get an LCD is so that we can put the numerators together. And I'm kind of trying to go slow here so that you guys are making sure to follow this, because I know it's hard without being in class and be able to ask a few questions. So if we get an LCD to put them all together over that LCD, we're just going to go ahead and do the denominator. The x squared times x plus h, the whole thing squared, in factored form. And up top I have the x squared minus x plus h, the whole thing squared. Now up top, you are going to want to write this out twice, FOIL this out. Exponents happen first in order of operations, so we got to multiply that out first before we worry about subtracting whatever our answer is. So it's all the algebra that's probably going to screw you up, not the calculus. Good?
So you're gonna expand the top but not the bottom?
Correct. We're going to expand the top and not the bottom.
How do I know to expand the top and not the bottom?
Because our denominators usually we want in factored form. And remember, our goal after we do some copy dot flip is to get rid of this h. So this guy's not going to affect us. Okay? So we have our x squared minus, and then I'm going to do a set of parentheses or brackets, whatever, like suit your fancy. And when I FOIL or do big distributive property on x plus h, when I get x squared plus 2xh, I would try and get used to this pattern, plus h squared. Or if like you really need to go on the side and do x plus h times itself, x plus h. First would be x squared, outside would be xh, but the inside would be another xh. That's where I collect them and get two of them, 2xh, and h times h is h squared. All over the x squared times x plus h, the whole thing squared, and then there's still all over the h. Isn't this lovely? Woo! This is good stuff. All right, so we're going to kind of scooch over here. I am going to erase my picture of how we got this whole definition of derivative thing.
No,
So
don't do it.
Hopefully that's in your brain. Erasing it. I'll keep the formula up there, but I need more space, right? I'm already limited, you guys. This is one board, and usually in my class I'm like always stringing across two boards. But we're making it work with our one nice board. So when I'm trying to find my derivative, f prime of x, in general terms, in terms of x, we still are carrying our limit notation because we're not ready yet. The limit as h approaches 0 of x squared, I'm going to distribute that negative through, minus x squared, minus 2xh, minus h squared, all over our x squared times x plus h, the whole thing squared, denominator, in factored form, all over h. Oh, and look at this. Nice things start to happen. Things without h's from the numerator are canceling out. Isn't that lovely? So now we have f prime of x equals the limit as h approaches 0. And our first fraction that we have, because now we really have one fraction over one fraction. You guys, this is h over 1. Our first fraction, with those x squareds canceled, is a negative 2xh minus h squared over this factored denominator piece. So I'm going to write that as my first fraction. I'm going to copy that down. Negative 2xh minus h squared over x squared times x plus h, the whole quantity squared. I'm going to change my big division into a dot for multiplication, and I'm going to flip or reciprocate h over 1 to be 1 over h. Cool. Woo! So now I probably want to look for some things to go away. But notice up top, if this is just a 1, these two terms have something in common. Just like they're supposed to. All the stuff without h's are supposed to cancel, which that happened. And everything that has left has an h in it. So if it has an h in it, but they're not like terms, can't I at least change it into factored form and factor out that greatest common factor of h? So I would have h times negative 2x minus h, right? H times negative 2x would get me back to negative 2xh. And h times a negative h would get me back to h squared. I don't need the 1 anymore. All over, maybe you want to move this h in front. H times x squared times x plus h, the whole thing squared. So again, this is why we wanted that denominator left in factored form, because we're really trying to get rid of the bad factor. You guys, the bad factor is the h. But now if it's h times all of this, h times x squared times all of this, can these h's as common factors reduce out? And if we were just able to reduce the h's out and our bad factor goes away, then that means now we should be able to drop the limit notation because we're ready to do direct substitution. Now we're ready to try to plug in 0, but remember plugging 0 in for h. So we would have negative 2x, no limit notation, minus 0 in the numerator, over x squared, because the h's here cancel, times x plus, I'm replacing every h we see with 0, 0 the whole quantity squared. So that will give us a negative 2x on top, over what? X squared, x plus 0 would just be x, and another x squared. So you'd have 2 factors of x here, 2 more here. Wouldn't that give us x to the 4th? So I have negative 2x over x to the 4th, but I still have like bases, 1 on top, 4 on bottom, 1 on top, 4 on bottom, leaves me with 3 on bottom. So my answer for f prime of x in general is negative 2 over x cubed. Remember, cubed is when you have to the 3rd power. And if we now wanted to find the derivative as a certain point, if I said, okay, now write me the equation of the tangent line when x is equal to 4, then you could find the slope at 4 by plugging in f prime of 4. Oh, so 4 cubed would be 64, and negative 2 over 64 would reduce to negative 1 over 32. Or if I said, I want you to find me the derivative at the point when x is negative 1, right? So instead of just finding the derivative in general, finding the derivative at a specific point, then you could say, oh, I want to find f prime of negative 1. And take this x and replace it with negative 1. Negative 1 cubed would still stay negative 1 times negative 1 times negative 1, 3 times in a row would be negative 1. And the negative 2 divided by the negative 1 would turn into positive 2. And then we would have the derivative when x is equal to negative 1. Which actually, even though I drew like kind of a crappy sketch, kind of makes sense. If x is negative 1, and I plug that in, wouldn't my tangent line be rising up? Its slope would have to be positive, and the curve is rising up. The little slope right at this instant is going to be the same thing as the slope of the tangent line at the instant when x is negative 1, and positive 2 sounds like a pretty good valid answer for that, just looking at it graphically. So we have this much more powerful formula that helps us, and we can still find the derivative at certain points. Okay? So we are moving on to example 3. So that one was more of fraction messiness, right? LCD to get one fraction over one fraction. So we could do a little copy dot flip. You're going to have a lot of stuff towards the end of the part 2 assignment where you're going to have to do fractions. So if you get stuck, re-watch this example on this video. Like, you can re-watch the video more than once and go through it kind of line by line with whatever your problem is. I mean, they're going to be the same basic flow, even if the numbers are a little different. It's the same basic strategy over and over and over again, right? You could re-watch the video. You could take notes. You could look things up. There are things out there to help you. All right, so moving on. So example 3 says find f prime of x, the derivative in general, derivative in terms of x, if f of x is equal to x cubed. So we're going to do 2 that are pretty similar to this, and you're going to see why, because it kind of builds. And it seems like a nice little problem. You're like, oh, that's just like the parent function for cubic, right? John Travolta curve, and you're like, yeah, like this is going to be easy compared to like the last stuff that had fractions or the stuff that like ended up being with radicals and conjugates. Yeah, we'll see. Here we go.
Piece of
f
cake.
prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. It really is the same thing as slope. This is like y sub 2, this is like y sub 1. And our x sub 2 was really x plus h, and our x sub 1 was x, but when we subtracted them, the x is canceled, and we just have the h left. Okay, it still really is the same idea as slope. You're just doing the limit as h approaches 0, so you don't really have any distance anymore, and you're finding the slope at a point, or the slope of the curve at a certain point. We're just finding it in general terms, in terms of x. So f prime of x equals the limit as h approaches 0. Well, f of x plus h just means go to our rule for f. Our rule is like little tiny, little innocent rule, x cubed, and we're going to replace x plus h where we see the x, and it's still going to be the whole thing cubed. Minus f of x. Well, f of x is just this one term. So minus x cubed If it were more than one term, we would have to do minus some sort of grouping symbol, so we would distribute the negative through. But we're good here. All over h, don't lose your h. So a lot of you are going to look at this and be like, okay, so the first thing we try with limits is direct substitution, but we know h going towards 0 on the bottom with direct substitution is going to give us division by 0. That's a big no-no. And up top, if we tried to plug in 0 for h, x plus 0 would remain x cubed would be x cubed minus x cubed, so it's 0 over 0. So we're going to have to finagle. So a lot of you are going to be like, well, now what? Well, now wouldn't you probably have to expand this, right? Cube it out. Write it out 3 times in a row and multiply it all out. I mean, you can't multiply it all at once, all out, but couldn't you FOIL the first 2 and then go ahead and take that answer and multiply with the last one? So I'm going to show that big expansion. So if I kind of come over here and go, it's x plus h times x plus h, which we just did on the last problem, right? It gave us x squared plus 2xh plus h squared. But I know I really want to take that answer because it's cubed and do times 1 more. So x plus h. Okay, so let's see if we can follow it from here. The x squared plus the 2xh plus the h squared times x plus h. This trinomial times this binomial. So we would get x cubed for the first, woo, right? We would get a 2x squared, because there's 2 factors of x, times the h, plus x times h squared. Good thing these are all plus signs. Plus x squared h from these 2, plus 2x h squared, because there's 2 factors of h there, plus h cubed. And I'm writing totally crooked. And that was just this part, minus the x cubed, minus that single term. And it would all be over h. So this looks like a big fat mess, but we know that there's like a pattern that keeps happening, and keep watching for this pattern. And the pattern is things that don't have an h should cancel out. Oh, lo and behold, this is a positive x cubed, and it cancels out with this negative x cubed, and everything else that we have has an h in it, right? So if everything else that we have has an h left in it, and for a minute it might really seem like there are like terms to combine, because this is x squared h, where this is x to the first power h squared, so those are not like terms. I guess right here we have one set of like terms. Here's an x squared h, here's one of them, and this with a 2x squared h, that would make what, 3 of them? 3x squared h's. And I guess right here we have some like terms. Here's a 1xh squared, here's a 2xh squared. So that when I add together, since they're both positive, would make 3 of them. 3xh squared. The variables and the exponents don't change when you just combine like terms. And then we just have our little cubic h cubed on the end. All over h. So everything without an h canceled, and then we had a few things that combined a little bit. And regardless, once you combine, even if you forgot to combine, when all of the things that will be remaining on the board have an h in them. So if they have an h in them, can't we factor out a greatest common factor of h? We can't factor out anything higher than that because our lowest power of h is the h to the first. So we'd have the limit as h approaches 0 of h times 3x squared plus 3xh, right? Here's one factor of h, here's another one to make the h squared, plus h squared to make a total of 3 when we remultiply, all over h. And now that we're in factored form, we have a common factor, and we just got rid of our bad factor. And we don't even have a fraction anymore. That's kind of nice. We didn't have to do anything with conjugates. Really, in order to make this work and get rid of our bad factor, we just had to multiply everything out. And so we're down to f prime of x equals, I'm going to drop the limit notation because now I'm ready to substitute, but remember I'm substituting a 0 in place of h. Here's a h to plug in the 0 to. You guys, this part doesn't have a h to plug anything into, so we have 3x squared plus 3x times 0 plus 0 squared. Well, anything when you're multiplying by 0 is going to go to 0, so these are going to go to 0, and this part's just going to be f prime of x, or our derivative in terms of x, equals 3x squared. So that worked out pretty slick, pretty nice. Okay? So in order to do problems when the power gets bigger, so on the next problem, we're going to still find the derivative in general terms in terms of x, find f prime of x, but I'm going to change this instead of being x cubed to x to the 5th. So if you were trying to just do the problem the same way we just did this last problem, you were like, okay, so this is to the 5th, and this would be minus x to the 5th, and we would have 0 over 0, and then you would say, Miss Ryan, are you kidding me? You want us to do x plus h times itself 5 times in a row? And I would go, yeah, and then you would laugh at me. And no matter what, like, you're guaranteed to make some dumb mistake. Like, some of you might have made a mistake here just trying to cube it. So there is kind of this shortcut way. It takes like a little bit of explanation, but I'm going to try and explain it to you because you're going to need to know it for homework, and we're going to go back and do this problem the shortcut way, and then you'll see how this problem works with the shortcut way. Some of you maybe have seen this before. If we had a class, you know, that was like, I don't know, some random upper level class sometimes where we had more time and we weren't so restrained by keeping a pace, we would probably discuss Pascal's triangle. But there's this thing called Pascal's triangle. So it helps us when we are expanding quantities, okay? So they always, or at least the way I've always seen it, and Mr. Hardy can jump in here at any time, are kind of thinking, okay, if I were doing a plus b to the first power. So I've seen it where they use a's and b's. It doesn't matter if it's a's and b's or x's and y's or x's and h's. It's kind of the idea of like the coefficients, and you get the coefficients down, and then you go from there. So wouldn't this be 1a plus 1b, or a plus b kind of to the first power, right? And Pascal's triangle, you can always like kind of create, and if you like know how to create it, then you can build it up as many rows as you need for expanding something to the 3rd, like we did here, or to the 5th, like we're going to do next time, or to even the 10th power, let's say. So this is kind of like the first level of Pascal's triangle. Well, the way that you build it up is it always starts and ends with 1. So that's kind of nice. Oh, the coefficients on the beginning and on the end are always 1s. Yep. Because it'd be like a squared and b squared, or a cubed and b cubed. That's a 1a squared or 1b cubed. Or a to the 5th and b to the 5th, right? So that's not bad. So if you know you start and end with 1s, the way that you get the next number on the chart is you add these two. So 1 plus 1 is 2. So actually this 1, 2, 1 represents a plus b the whole thing squared. If I wrote that out twice and FOILed it, wouldn't I get a squared plus 2ab in the middle plus b squared? Oh, look at that. They're the coefficients of what I have going right down kind of in like order. Cool. So if I know I always start and end with 1s, these are going to be 1s. And then the way I get this stuff in the middle is I add 1 plus 2 is 3. 2 plus 1 is 3. So 1, 3, 3, 1 really represents a plus b, the whole thing cubed. And believe it or not, you guys, that's what we got over here. We got a 1x cubed. When we combine like terms, we got a 3x squared h. We got a 3x squared. So like your one variable is going down in power, your other one's going up in power. And we got a 1h cubed. I mean, our x cubes like eventually canceled here, but like if I would have just combined. Cool. So that's what we got. So the next row would start and end with a 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Oh, so if I were expanding a plus b the whole thing to the 4th, or whatever the letters would be, it would be a to the 4th, just one of them, of 4, so I'm going to write it, of 4a cubed, because this is going to go down in power, with a 1b, a 6 as a coefficient, a squared, this one's going down, this one's building up, b squared, a 4, a to the 1st going down in power, a b to the 3rd, and then this would be a 1, b to the 4th. That's how it really goes. So it's telling you the coefficients in front. Okay? And the only difference is if this were minus instead of plus, the signs would alternate. So it would be a to the 4th minus b, 4a cubed b, plus 6a squared b squared, minus 4ab cubed, plus b to the 4th. The signs would alternate if it's minus. It's going to be plus for you guys because we're doing x plus h. So if we're doing to the 5th, oh wait, Mr. Harney's.
So if it was minus, guys, I would always just treat it as like a negative b. Because then it would be negative b to the 1st, so that would be a minus. Negative b squared, that's why it's positive, because negative times negative is a positive.
Okay, that's good.
And so on. So you could just, and you could make these a lot harder where you have not just a here, but you have maybe say 4a. Then you would have 4a all as your first term. So you'd have like 4a to the fourth and 4a to the third. And then you could expand that and get super crazy stuff going on.
That's for a bigger lesson on Pascal's triangle. We're doing like the pretty basic. So remember, we're eventually going to want to do x plus h to the fifth. So we're kind of on that like fifth row. So remember, we start and end with a 1 always. And then we get the numbers in the middle. You take this 1 and you add it to this 4 and that becomes a 5. You take this 4 and add it to the 6 and that becomes a 10. You take this 6 and add it to a 4 and that becomes a 10. This 4 and 1 would become a 5. And I had the 1 on the end to end with. So I have a 1, 5, 10, 10, 5, and 1. They have like patterns that you'll see. Oh, so if I'm really expanding it, and I'm trying to use Pascal's triangle, and I'm going back to my problem, right? So that I can find the derivative in general for f prime of x if f of x is equal to x to the fifth. So I already have my definition of derivative, so catch up with me if you're not here. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. I went ahead and plugged in my x plus h in terms of my x plus h to the whole thing to the fifth minus x to the fifth all over h. And since it's just one term, we can just do minus that one term. But now I'm ready to do the expanded part. But instead of really having to write it out 5 times in a row, and with that 5 times in a row, multiply it out the first 2 times, then multiply it with the third one, then multiply it with the fourth one, then multiply it with the fifth one. Because you're just like guaranteed to make some sort of mistake, right? Combining like terms or with your exponents or whatever. Wouldn't this still be the limit as h approaches 0, x plus h to the whole thing to the fifth, look at Pascal's triangle, would be 1. The 1 would be representing x to the fifth, 1x to the fifth. This is plus, so all the signs are positive, plus 5. Oh, we would come down in power on the x's, x to the fourth, because we're going down 1 degree, but go up 1 degree for h. So h to the first, because this is like h to the 0 right here. Plus 10. The 10 would be 10, go down in power, x cubed, go up in power for h squared. Just like we would with a's and b's, just like we would if it were x and y. Plus another 10. Oh, plus another 10. 10x squared, h cubed, right? Coming down in power on the x's, going up in power on the h's. Plus 5, 5x to the first, which probably we're not going to write x to the first, we're just going to write x, and go up in power for h to the fourth. Plus 1, and the 1 just means h to the fifth, 1h to the fifth. So that's just the Pascal's triangle part. But then we have, don't forget this guy, minus x to the fifth power. All of that's the numerator. But instead of having to write it out and multiply it out to get that product, we're using Pascal's triangle to make that shorter. And we still have all of that divided by our bad factor of h. But now aren't we looking for things that are going to cancel? And actually things should cancel that don't have an h in them. And lo and behold, the things without an h in them cancel. And maybe now we look for some like terms. So I don't have any other h to the fifth, so he's still going to be there. This is h to the first, this is h squared, this is h cubed, this is h to the fourth. Oh, those are all different powers on the h's, and they're all different powers really on the x's as well. So we don't really have any like terms to combine, do we? So maybe we don't have like terms to combine. But if they all have an h in them, how about we factor out the greatest common factor of h? Notice my limit notation is still there. I haven't evaluated the limit yet. I haven't got rid of the bad factor yet. So if I took out h to the first power, what did I have? 5x to the fourth left. The h is already there. It's already accounted for. Plus, when you are undoing a greatest common factor, pulling it out, you're just undoing the distributive property. 10x cubed h to multiply back with this h to make the h squared. Plus 10x squared h squared, because here's that third h, plus 5x h cubed plus h to the fourth, right? That looks like what we would have left, because if we redistribute, we would get back there. All over the h. So I'm just going to erase this, where I was kind of writing that a plus b, the whole thing to the fourth, out in expanded form. All over h. And then we're super excited because we're like, our bad factor went away. The h is canceled. We're in factored form, so we can cancel out those common factors. And if we can cancel out those common factors, then that means we're ready for direct substitution. So we would have f prime of x. If we're ready for direct substitution and to plug in 0 for h, then that means the word limit goes away. We are evaluating the limit. I don't even really need parentheses around all those terms. So they're all up in the numerator. They don't have anything to do with each other. So 5x to the fourth plus 10x cubed h. Oh, I'm replacing h with 0. Plus 10x squared h squared, 0 squared. Plus 5x h cubed, 0 cubed. Plus 0 to the fourth power. No fraction bar anymore because our bad factor in our denominator went away. We don't have a fraction anymore. And all of these things, when we're multiplying with zeros, are all going to go to 0. This is going to go to 0. This is going to go to 0. 0 to the fourth is 0. So the only thing we have left is our one measly piece in front. So by definition of derivative, f prime of x, the derivative in general, in terms of x, of the original function, x to the fifth, went down to 5x to the fourth. And we found it with that more powerful formula. Okay, so there's a little lowdown on Pascal's triangle, which I know is kind of intense. I think you just have to use it maybe once. It is something cool that you can see that you can build if you ever need to build it to expand something to a high power that's a two-termed binomial. Mr. Herney, do you have anything to add past there?
Is Pascal a physics guy? The physics guy?
Herney loves his physics.
He is.
He's a physics guy?
Yeah.
Okay. Are we good?
Pressure is named after him. A Pascal.
There you go. All right. See you guys later.